Welcome to Engineering Innovations, the official podcast of Purdue University's Elmore Family School of Electrical and Computer Engineering. I'm Kristin Malavenda. Today's episode is a first for us. Instead of featuring a faculty member, we're talking with a PhD student. Connor Devitt is the lead author of a new paper in the journal Nature, demonstrating the world's first on-chip, tunable spin wave ladder filter, easy for you to say, for future 5G and 6G communication systems. So we're going to talk about what that actually means and what it's like to spend 4 years pushing a device from concept to fabrication to publication. Connor, thanks so much for joining me today.
Yes, thank you for having me.
Let's start, though, with tell me a little bit about where you grew up and when maybe you first realized that engineering might be your path.
Sure. So I grew up in the suburbs of Philadelphia in a little town called Glenside. And engineering was never a question of if.
Okay.
I think my parents and grandparents always joked that it was not if I was going to become an engineer, it was what type of engineer.
Gotcha.
So when I was running through school, I would build like little games in Java or build model rockets.
Yeah.
And I was always attracted to this type of tinkering and inventing and engineering.
Are your parents engineers?
No, but I think my mom was trained as a packaging engineer.
Okay.
But she doesn't do engineering now. No.
So electrical engineering just grew out of what your interests were?
Yeah, so I think it really solidified like in my high school. So I was part of the first robotics team in high school.
Yep.
So I would have my hand at like different aspects of robotics, whether it was kind of mechanical engineering, constructing the actual actuators and frames and machines to interact with objects, to programming the robot, designing the interfaces between all the sensors and actuators and motors.
Gotcha.
And I also had a couple of internships as a software engineer during high school where I would develop codes to track printed circuit board assembly through the manufacturing process. And I think from those two experiences combined, I found that the most satisfying thing for me was to see kind of the code that I'd written work in front of me as robotics. And I think electrical engineering gave me the best opportunity to continue doing that type of robotics.
Great.
At the time. Yeah.
That makes sense. How did you end up at Purdue and then with the Oxide MEMS lab?
Sure. So, in the end of my master's degree, I was going into my final year, and I wasn't quite sure what I had wanted to do, whether it was continue on to do a PhD or go into industry. And at the time, I didn't have too much research experience. It was mostly just coursework up to that point. So I thought in industry, it would be a much safer opportunity.
Yep.
I'd get paid pretty well. I'd get to do something pretty interesting for a few years, and then later on, I could decide if I wanted to do a PhD. But during the course of my final year in my master's, I had really loved the research I was doing. It felt really novel and interesting to kind of explore new ideas. So by the time I graduated, I know for sure that I wanted to do my PhD, but it was too late to apply.
Okay.
So I worked for a year in industry designing beam-forming networks for antenna arrays. So you could electrically steer radiation patterns. And after a year went by, I started applying for PhD programs, and I got one offer from my current advisor, Sunil, and he sent me this paper on chip-scale magnetostatic wave resonators. And to me, this was kind of groundbreaking because all my training before had been as an RF electrical engineer.
Right.
So I was used to dealing with electromagnetic waves. And these waves are, they've got linear dispersion. So if you want to design a circuit at 10 gigahertz, that frequency would dictate the size of the circuit, the dimensions, everything.
Right.
And if you want to design a very similar function circuit, but maybe 2.45 gigahertz, everything changes. You have to start the design process over again. And this paper kind of broke that convention for me.
Okay.
Because in spin waves, the dispersion is not linear, it's very flat. So the dimensions of a circuit that you design at 10 gigahertz could also work exactly the same way at 2.45 gigahertz or 15 gigahertz and so on. And the only thing that changes is maybe the magnetic field that you apply.
Gotcha.
And this was really attractive for me and was incredibly interesting because it could kind of enable many new devices.
Yeah.
And I was instantly hooked. So I decided to join Sunil's group and study spin waves.
Great. So When people hear PhD student, I think they think of someone like in a windowless room, like, on their computer 24 hours a day. What is your day-to-day like as a PhD student?
It's actually pretty diverse because I'm experimentalist. So I'll do a lot of testing. I'll do fabrication. So in that way, it's I'll have some days where I'm doing derivations and writing code to do some finite element simulations or Python simulations. But that's a given. But some other days or months at a time, I'll be working in the clean room over in Burke on the other side of campus, where I take some designs that I had simulated or we finite element or Python or whatever, and I'll design lithography masks and actually make the devices that I've designed, and that's pretty satisfying.
Yeah.
And then once I'm done with all the fabrication, I'll actually go to the other side of campus and I'll work in a lab. It does have windows.
Good to know.
And I'll do a lot of characterization and testing. And a lot of this is kind of set up. So I might spend a few days carefully designing experimental setup to test a particular hypothesis or to do a certain type of characterization. And then kind of just a lot of measurement.
Yeah.
Yeah.
So how much it sounds like you have quite a bit of hands-on stuff you're doing too, but how much of your work is theory versus hands-on?
It's almost all hands-on.
Oh, great.
So I don't really work to develop any new theory.
Okay.
I think most of us in this lab, we try to invent new microfabrication processes, and using those microfabrication processes, try to make a design or some type of device that wasn't possible previously.
Gotcha.
And we leverage existing theories of how these work.
Okay, that makes sense. So as I mentioned in the opening, you recently had a paper published in the journal Nature detailing how you and your colleagues developed a new chip technology that could shape the future of 5G and 6G. So give me an overview of what problem you were trying to solve with this research and what solution you came up with.
Sure. So we were mainly focusing on wireless communication, mobile communication type of application in this paper. And the big key here is, moving into the future, wireless networks are going to be transmitting much, much more data than previously.
Okay.
So in order to accommodate this extra network capacity, you need to allocate additional spectrum. That's one of the simplest ways to increase data throughput. Yeah. And in particular, there's this new frequency spectrum called the upper midband or frequency range 3, from about 7 gigahertz to about 24 gigahertz. Okay. And by comparison, current wireless communication happens mainly below 6 gigahertz. So this new spectrum is much wider, and can accommodate much more data throughput. But we need hardware to support this new spectrum. So I'd mentioned, before, if you want to design a circuit at 10 gigahertz, it's its own design, and 2 gigahertz its own design. So all the circuits designed sub 6 gigahertz have to be redesigned for this new spectrum. And that creates a problem because most of the wireless communication systems today, especially the RF filters, are designed using mechanical waves.
Okay.
Or the mechanical devices. So there's a piezoelectric film that vibrates, and there's a transducer which takes the electromagnetic wave into a mechanical wave and then back out to electrical wave. And the filtering happens in the mechanical domain. But these mechanical devices don't scale well towards higher frequency.
Okay.
It takes significantly more work and more engineering to keep the same type of high filter performance. Low attenuation for the signal of interest, high attenuation for signals out of band, and many more types of figures of merit. And also they're fixed frequency, just like electromagnetic waves. So once you design a mechanical filter, it can't be tuned in frequency.
Okay.
So this wide spectrum allocation from 7 to 24 would mean that you need many individual mechanical filters. And especially with mobile devices where space is very heavily constrained, it becomes an issue. Like, how do you fit so many mechanical devices into a very confined volume?
Right.
And we thought spin waves could offer a solution where instead of having hundreds of mechanical filters, you could have just a handful of tunable spin wave filters.
Gotcha.
That could cover this entire frequency range.
That makes sense. So instead of having a bunch of individual ones for each frequency, you have one that you can tune, like a radio station or something like that kind of thing?
Yeah, exactly, yeah.
Okay.
And it's easier said than done, of course, because this has been kind of the holy grail of RF engineers for a very long time.
Yeah.
Like, how do you design a tunable bandpass filter? It's a very difficult problem, and many people have tried to tackle this using electromagnetic devices, piezoelectric devices, hybrids, all sorts of these things. So the fact that we were able to achieve a tunable spin wave filter is quite a nice achievement, and kind of sets a path forward towards eventually realizing this type of wireless communication. Yeah.
So as part of this research, you built a frequency-agile radio. What is that, and what was the process of building it?
Sure. So, it's one thing to show frequency responses and figures of merit in a paper, but we wanted to push this kind of one step further and demonstrate the filter working in a radio itself.
Yeah.
And the radio that we had developed is a skeleton version of what a relay system might look like. A relay system would have, a transmitter and an antenna and like a wireless channel, and then like its own separate receiver.
Yeah.
And the electronics are much more sophisticated. So we tried to simplify this very complex radio system into something that would be suitable for a demonstration and show kind of the merits of our filter. So we had, I had taken a random bit stream of data. It was just random. We didn't care about what data we transmitted, just that it was some binary strings of data. And I grouped them into groups of bits, and assigned a waveform to each grouping of bits.
Okay.
And depending on the phase and amplitude of this waveform, I would know that this is a 0 bit or a 1 bit, and so on. And then I would upconvert it to gigahertz frequencies.
Okay.
Send it across a wireline channel into a receiver, which on the same tabletop, but on the receiver side, it would go through our spin wave filter and then get demodulated down to near DC, and then I could recover the bits I transmitted.
Okay.
And the key things we wanted to show were, if you don't have the spin wave filter on, you turn the magnetic field off.
Okay.
Then you shouldn't be able to recover any of the bits, meaning that the spin wave filter attenuates all the signals pretty equally.
Yeah.
And any information or interference that you transmit across the channel should be very strongly attenuated. And we were able to show that. And then the moment of truth is when you turn on the magnetic field and tune the magnetic field so that the data that you were transmitting at maybe 10 gigahertz, you have the spin wave filter also aligned to 10 gigahertz. We wanted to show that you were still able to recover the information. And we did that. So the information was successfully transmitted through our spin wave filter and recovered at the receiver. And then the real key here is, can we tune the radio's frequency and spin wave filter synchronously in time, so that at any frequency you want to transmit that, you can still recover the data. And we were able to show that. And I think it's really nice. Nature allows us to submit videos.
Yeah.
So in the supplementary information, we actually have live video of this radio working.
Oh, cool.
And I think any undergraduate or graduate that's taken like a digital communications class would find this really kind of a nice demonstration, because it aligns very well with kind of the coursework they might be doing. So they would be studying this type of radio transmitter in their course, and then they could go online and download a video and see it working in real life.
That's awesome. So how does this change? We're all worried about our smartphones. How does this change the future of smartphones?
Sure. So I think the demonstration of our ladder filters is very kind of early. It's going to take quite a bit of effort and engineering to mature our technology to the point where it could be integrated into a cell phone. That being said, if you look very far into the future, this type of device, if you make it small enough, could be integrated into your cell phone and enable you to do kind of dynamic wireless communication, where there's a lot of interference. The spectrum is very crowded. So maybe 10 megahertz away, somebody's talking very loudly, and that creates a lot of interference. And because of that interference, you might not be able to transmit data as quickly or as reliably.
Right.
And this type of filter enables you to dynamically change the frequencies that you're talking at. So, for instance, if you're observing a lot of interference at that particular frequency, you can just move to a portion of the spectrum that isn't being as actively used.
Gotcha.
And potentially have higher data rates and more reliable communication.
Is that similar to what this means for 6G?
Yeah, exactly. So you can do these reconfigurable wireless communication applications where you're dynamically changing center frequencies to kind of get the best data rates. Or, like I said, you could use these tunable filters to potentially replace, large arrays of fixed frequency filters, giving you maybe, on a system level, maybe better power efficiency. For example, maybe better, efficiency in terms of the volume of your packaged device as well.
Gotcha.
Yeah.
So, how long did this project take?
So this has been going on for many, many years, actually. I think it's been over 5 years of collaboration between Purdue and BAE Systems to develop and push this technology. But this particular program started just before I joined Purdue.
Okay.
And I've been working on it ever since. And I think the key moment for us was in the first maybe 3 years of the program, where we were working very hard to develop just a single spin wave resonator, which is a fundamental building block of a larger filter.
Okay.
And for us, we knew kind of the performance that this resonator would need to kind of be a very nice filter. And there's two maybe main figure merits for these types of spin wave resonators, and that's by quality factor and coupling. And we want both to be as high as possible. Okay. So the quality factor eventually translates into signal attenuation for the filter. Yep. And the coupling would eventually translate into the bandwidth of the filter.
Gotcha.
And initially we had quality factor. These spin waves are very low loss. They work very nicely. But the problem was always the coupling. Okay. And we weren't able to get enough coupling to realize a filter with sufficiently large bandwidths for these wireless communication applications, until one of our collaborators realized if you could put a ground plane beneath our magnetic material, very close, like a couple of microns. Okay. Then you can get sufficiently high coupling and quality factor at the same time. And since then, we had been working very hard to develop a new microfabrication process, where we do surface micromachining on the top side of our chip, and where we have all of our RF electronics. So we have the active magnetic material, and we have all the signal routing on top. And then we flip the chip over. Okay. And we do very deep bulk micromachining to thin down the chip in selective regions so we can get this ground plane very close. Okay. And we were finally able to demonstrate like a couple of devices on the chip, maybe like late 2023, early 2024. And those devices showed really nice quality factor, really nice coupling. It worked amazingly. Yeah. But then there's still some challenges to kind of take those hero resonators and turn them into a filter. Okay. Namely, the fabrication process, we were able to demonstrate just a couple of devices, but we would need much higher yield. Okay. It has to be much more reliable and repeatable. And secondly was the filter topology. So there's a number of filtering ways to make a filter out of individual resonators, and we took some inspiration from the world of electromagnetic filters and also the world of mechanical filters. And we had tried a number of topologies, but we were never able to achieve the type of filter performance we really needed or wanted. But in the mechanical world, they use these ladder filter topologies, where you have two different resonators. Okay. And the resonators have very slightly different dimensions, so that they have different resonance frequencies. Okay. And that is absolutely key. So if you arrange these two resonators in a certain configuration, you'll realize a bandpass filter type of response. And it's very easy to do this in mechanical devices because they've got some nice dispersion. So you change maybe the thickness of your piezoelectric, you'll get a frequency shift, and that's that. Doing this with spin waves was very difficult. Okay. So like a change in dimensions for a resonator produced a very, very small change in resonance frequency, not nearly enough to realize these filters that we wanted to do. So we thought for the longest time ladder filters were just not really feasible in our material platform. we thought we would need two different magnetic fields to get this resonance frequency separation, until eventually we realized there is a term that we hadn't been accounting for before.
Okay.
And that was shape anisotropy.
Say it again?
Shape anisotropy.
Okay.
So depending on the shape of our resonators, there would be like an extra magnetic field.
Okay.
And we weren't accounting for that. And once we started to, we realized the ladder filters are possible. And by using the shape anisotropy, we'd be able to realize this with just one external magnetic field, which would vastly simplify the packaging and make these from impractical or impossible to kind of, we could do this.
Yeah.
So I spent, maybe the first half of 2025 just fabricating these devices. They take a very long time. They're very difficult. But eventually we realized a couple of devices, had them tested at NIST in Denver, and they showed very nice performance, just as we had hoped.
Great. Yeah. I can see, like, in your eyes and when you talk, how excited you get about these kind of discoveries. So tell me, what does it feel like to go from an idea to a physical fabrication and then having that work published?
It's deeply satisfying. There's something special about taking a design on paper or on your computer, you just see a 3D model, to having it in the palm of your hand and see it work.
Yeah.
So when I first landed our RF probes on this device and I saw the filter response, it was very special. I sent a screenshot to my advisor.
Oh, nice.
And we all celebrated. So yeah, it's really incredible to take a design for like concept to implementation.
Yeah. So have you thought about, you've been in industry for a year and you've been in academic research. Have you thought about past your PhD, which direction you want to go?
I'm giving it some thought, and I don't have a clear direction yet.
Gotcha.
I really want to continue working on spin waves, and I want to find a direction that would let me continue doing very interesting new research.
Okay.
Whether that is something that industry can afford me or academia, I'll decide later.
Gotcha.
Yeah.
So you want to keep doing the research you're doing now? What other areas maybe do you want to go into?
Yeah, so spin waves are an incredibly deep topic. I think I could study it for my entire life, and it would never end. Be fascinating.
Yeah.
But I think right now we're focusing, or at least I'm focusing, on characterizing some of these devices in a little bit more detail, studying how they perform over different geometries, and also studying how they perform under different power conditions. So these devices show some interesting nonlinear effects. So I'd like to characterize those and maybe formulate different applications that we could use those nonlinearities for.
Gotcha.
And then on the other hand, I'd like to kind of focus more on system level. So taking this from, just in a lab and integrating these devices into a larger communication system.
Right.
Eventually realizing maybe some of these frequency-agile systems.
So as a PhD student, what's your interaction with your advisor like? How do you work with your advisor?
Sure. So Sunil is very hands-off. He lets me explore ideas in my own pace and in my own way. And he's more of a guiding force. So he'll kind of steer me in the right direction, and he'll kind of maybe propose some wild ideas for me to consider, and maybe some analogies from other domains to consider. And then I can go and explore those on my own. Yeah.
What a lot of research is failure.
Yes.
So what happens when you think something's going to work and then it doesn't? How do you kind of get around that?
Yeah, so I mean, we've had failures every step of the way. And whether it's from device design, like topology and system level design for the filters, I've tried so many different ways to make these filters work. And I think in that regard, we just have to keep trying and either show that it wasn't possible or find that one kind of path towards something that's realizable. But we also had failures in fabrication. And those are a little bit more tricky or a little bit more demoralizing.
Yeah.
Because I'll spend maybe a month in the fab to make a chip, and then it might fail in the very last step.
Yeah.
But I think for those, as long as if I can discover the reason why it failed.
Yeah.
As long as the failure wasn't without purpose, I think it's completely fine. Yeah.
So, what's been the most surprising part of your PhD program?
I think the variety of ideas that I've been exposed to at Purdue has been incredible. I wouldn't have imagined it. We have people from all these different disciplines, and they all give research seminars. And I love going to those.
Yeah.
Because they come up with ideas solutions to problems that I didn't even know were problems in the first place.
Right.
And their ideas and their research isn't just limited to their domain, but could have analogies or applications to my own research.
Right.
So it's always fascinating to kind of see what other people are doing at Purdue.
Yeah, things aren't really in silos anymore. Everything overlaps and interacts. So, what advice would you give to an undergraduate who is considering going for a PhD?
Sure. I think a PhD takes a very long time, and that's an incredible amount of work. So if you're going to do a PhD, you make sure you understand what you love to research.
Okay.
Because if you don't like it, it's going to be very difficult to make it all the way through. And then maybe the second is it's okay to wait to start your PhD. So you don't have to go right out of undergrad and start your PhD. It might be okay to take some time, explore what there is in the world first, and then return later.
Yeah, figure out what you like and then come back and study it. So.
Yeah.
So when you're not in your lab with Windows or researching or fabricating, what do you like to do in your free time?
Sure. I like to play music. So I play bass and I play guitar.
Okay.
And I like doing that in my free time. And hiking. I like to hike.
Awesome.
Yeah.
Well, thank you so much for joining us, and congratulations again on your publication in Nature.
All right, thank you very much.
So this is exciting, not just for Connor, but also for Purdue ECE and the future of wireless communication. And what I loved about this conversation is it shows innovation doesn't just happen at the faculty level. It's happening in our labs every day, driven by graduate students who are designing, fabricating, testing, failing, and refining, and ultimately building the technologies that will shape 6G and beyond. If you'd like to learn more about Connor's work on spin wave bandpass filters for 6G communications, you can find the full story on the Purdue ECE website. Thanks so much for listening to Engineering Innovations. Don't forget to like, subscribe, share, leave a review. You can also leave a comment about a topic or a person that you'd like to see on the podcast next. I'm Kristin Malavenda. I'll be back next month with another new episode.